Welcome to the office. We want to take a look at cyclic groups, starting to take a look at some theorems here. So let's take a glance. Elementary properties of cyclic groups, fantastic. So our first elementary property is that every cyclic group is abelian. If you don't want to see the proof, you're all set. Move on to the next video. But if you want to see the proof, if you would like to continue to improve your skills through exposure of other people's techniques, or right, there's the same general collection of techniques. But anyway, so let G be a cyclic group generated by an element of the group G. Now I'm going to add some lines in here just to make sure that I am staying well organized. Look at that. Right? See, that's not straight at all. All right. Anyway, let G be a cyclic group generated by some element in it. Next, we want to let, I don't know, let's call them X and Y belong to G. Since G generated by A is cyclic, we have we can say that X is equal to A to the M, and Y is equal to A to the N, for M and N being integers. Cool. Now, we got to remember what we're trying to show here. So all I've done is make some assumptions and just kind of specify what some things look like. The assumptions, or the assumption is that G is cyclic. That's it, right? Every cyclic group is abelian. So we assume that G is abelian. We assume that G is cyclic, and then we're going to show that it is indeed abelian. Now, you got to remember what abelian means. It means that it's commutative. So if we have a commutative binary operation, that's what we're looking for, or that's what we want to show here, then what we need to do is we need to show that x times y is equal to y times x. In order to show that x times y is equal to y times x, I need two elements, x and y. So I say, all right, well, let's let x and y be elements of G. Specific elements? No, generic. We want to show that two elements, no matter what they are, commute. Therefore, we can conclude that the group is abelian. So again, the operation would be considered commutative, whereas the group is considered abelian. Maybe that's a correct distinction. Anyway, so I've assigned x and y. We have x is this and y is that because it's cyclic. Then x times y. Excellent. So if I want to show that x times y, I'm using multiplication here as the operation. We could have used addition, in which case it would be m times a and n times a. But anyway, so multiplication is the notation that we're using. This may be written as a to the m times a to the n. And we know, based on what we've been given already, that this is a to the m plus n. So that's fantastic. But of course, addition itself within the integers is commutative. So this is a to the n plus m. And by recognizing that, we have that this is a to the n times a to the m. And finally, a to the n is y, and a to the m is x. So through our representations of x and y, we were able to find that x times y is equal to y times x. Thus, G, the group G, is abelian. Fantastic. Don't forget to indicate the end of the proof, and we are all set. That's it. So every cyclic group is abelian. How wonderful is that? All right. Join me back in the office for a little bit more on cyclic groups.